That's cool. Actually, I thought that zipper was a silly one to have as an example sound, but maybe I was wrong. I let other people make those decisions. I'm just an engineer. Yeah, well, we'll see. It may not be easy. A lot of those things, don't work the way you expect, but it might be something, just guessing, if you have that physical model, the kinetic thing, and then you feed that into a really resonant filter, like something that has the frequency, so that you get this burst of energy and then, going in all the time, but then you have a resonant frequency that's real strong. Maybe? I don't know. At least on my shoes, it always seems to be about the same pitch squeak. It's not... Oh, I'll never be a Mandalorian. All right. Oh, it's time. I can hear you. Thank you, Ramsey. Okay. Today, it's lecture 5. We're still doing history stuff. The main topic today is going to be this phase oscillator. Now, phase oscillator is a name I came up with. It's really difficult because there aren't really standardized words. There's about maybe a dozen different ways to make oscillators. But some of them have a phase register in them, and that's the ones I'm talking about. So it's called a phase oscillator just because there's a phase register in it. It's a word I made up. You're going to hear other names for things like, in this case, this could also be called a wavetable oscillator because the wave shape is in a memory table. And, wavetable oscillator and wavetable synthesis is a name that lots of people use. But actually, that's not the part of it that I find most interesting or most important. Does it have a phase register or not? Most important, like, for instance, the oscillators in the Haken matrix, there's granular-based ones, and then there's ones, there's lots of ways to make oscillators. You can do them with narrow bandpass filters and all sorts of other ways, too. But in the Haken matrix, the main oscillators that you use are actually not wavetables. They're math functions here. A subclass of math functions called digital summation formulas. But so they're not wavetable oscillators, and I needed some word for, hey, what are the issues in just a digital oscillator that has a phase register? And I would say this gives you really good insight into lots of the fundamentals of electronic music and digital implementation of electronic music. So, it's not the heart of every digital synthesizer, but it is the heart of many of them. And it's also, the ideas are really, really important. What else can I say about this? One thing you do know about any waveform that repeats, like this phase oscillator here, is made for making a repeating waveform. Let's see what I wrote here. Thought I wrote it down somewhere. Anyway, so like say you have a sawtooth. That's really common, or a square wave. A sine wave. Sine waves are actually easier, but there's whatever waveform you've got, it exactly repeats. What do you know about the frequency ratios of harmonics in exactly repeating waveforms? I brought this up before. I don't know if it made sense, but if you have a waveform, I'll go to the bottom of the page here. This is just an aside because it's come before, and it's one of the ideas that you'll see here too. But here are sawtooths made with different number of sine waves. So they're approximated with 1 sine wave, 2 sine waves, 3 sine waves, 4 sine waves. What you'll notice is that, this one is just a fundamental frequency, but here you have exactly twice the frequency and 1 times the frequency. Here you have integer number, 3 times the frequency, 2 times the frequency, and 1 times the frequency. Here you have 4 times, 3 times, 2 times, 1 time. But these are exact integers. And every repeating waveform that you can make is made up of exact integer multiple frequencies. You can't have anything else. And if you think about it, like say in this one you had one that was 2.5 times the frequency. Well, the thing wouldn't repeat, right? Because instead of going through twice the upper one in one period of the fundamental, it would go through 2.5 times, and then it wouldn't it wouldn't be at the same spot that it started with at the beginning. So anyway, so to somehow convince yourself that's true, because that's a really important factoid. That any exactly repeating waveform has only integer number harmonics. But there's other weird things you're going to run into today which don't make immediate sense. Like if you have a waveform that's exactly repeating in analog, it'll never be, well, okay, you can think of a corner case, but it'll never be exactly repeating in digital. And that's weird. And a lot of people miss that. Even very smart professors and stuff I talk to, they just don't think about, the practical implication of these things. So again, I'll repeat that. If you have an exactly repeating waveform in analog, it won't be exactly repeating in digital. And actually, you know this. Say you had a sine wave generator in the lab, and you sampled it. Right? Well, every period of that sine wave, you hit different parts of the sine wave when you're sampling it. And, that's an exactly repeating sine wave. But when you're sampling it, you hit different parts of the sine wave each time through. Now, there's this weird corner case of, my sample rate divides exactly into the frequency of the sine wave. Well, that's like doing a coin toss. You say heads or tails or sides. Well, nobody ever chooses sides because that doesn't happen. I mean, I guess theoretically, maybe a coin could balance on its side and could land that way, but nobody worries about that. Right? So the fact is, again, if you have a sawtooth generator in the lab, and you take samples of it each period, you are going to get different sample values each period in digital. So if you're doing the reverse, if you're generating the sawtooth in the digital realm, right, you can't be generating the same samples every period over and over again, or it's going to be the wrong thing. It's not going to be the right thing. Are we good? Does that make any sense? All right, so, okay, so that's sort of some introductory stuff, just stuff to think about, because it's a background for this thing that ends up being really important. Before I go on with that, are there any questions here about the homework? People do okay? Sort of figured out? Okay, I'll just yak about it some, because the last thing I want is you people that come in person to feel like, hey, I'm going to call on you and make you talk at 8 in the morning. I'm glad you're here. So I'll just yak about it and chime in or raise your hand or whatever you want if you want to say something or ask something. Some question comes up. So yeah, so this was this initial graph, and one of the interesting sort of things here is, hey, this vertical axis is linear amplitude. Now, we almost never use linear amplitude in engineering, right? We say dB or something. And even in audio, boy, I often use RMS amplitudes or dB or some other units. But when you're doing timbre, when you're looking at, what does this sound like, it's really common to use linear. Why? It just turns out it sort of shows the right details. One of the things that happens is if we had dB, you'd see a lot more stuff out here where it's, where you see very little. Now, to some extent, maybe that would be good. You got to remember, too, this was done in an age of reel-to-reel tape recorders when there was quite a bit of noise and signals and stuff. So they would be covered up down here. And in modern times, that's what dithering is used for in digital systems, is to make a noise floor so that you don't, hear the too quiet stuff that you don't actually want to hear. That's a different thing. So what we got here is linear amplitude, and then in this direction we have seconds, and I pointed this out before, but this is a really short sound. This is 1/10 of a second long. A lot of it has to do with, even though these sound examples were put on reel-to-reel tape for the listening tests and stuff, they had to be computed at some point. And, when you've got memory that costs you $1 a bit and stuff, well, every little bit matters. And even if you're Stanford and doing fancy things, you still have limited resources. So that's kind of cool. There was this thing in this decay. These decays here, if you actually had an exponential scale, maybe they would be more linear. I mean, they look sort of, like exponential decays. But it is sort of curious here because there's this exponential-looking decay, and then you can sort of see it on this one too, but then it suddenly changes. Like, what is that? I don't know. My guess is you're blowing in the instrument here. This decay is sort of from inside the instrument. This is like you're starting to see reflections in the room, and they have different decay properties, but I'm making that up. I don't know. If anybody else actually knows this or has figured this out or has had some insight, that I'd be very interested. I don't know. But it's a weird one. But normally in synthesizers, too, for decays on amplitudes, you have a choice, linear or exponential, and exponential is really commonly used. It's just a common thing in resonant systems that they decay exponentially. You can see all these different exponential decays. You can wonder, hey, how do these exponential curves compare between the harmonics? There are things about like how fast do the harmonics come in? What are the onset times? Like in this particular sound, the higher harmonics actually come in kind of slow, which is unusual. Often in a lot of instruments, the higher harmonics come in right away and then die out right away. And they do die out faster here, but they also come in kind of slow. So it's kind of interesting. There's all this stuff about, I sort of made a list so I wouldn't forget here. There's these random variations. And how much of those random variations in amplitude are correlated between all the harmonics? And how many of them are really different? Every harmonic doing its own thing. Or every partial doing its own thing. I don't know. It's something to look at, though. They did straight line approximation of these things in the article, which gets rid of all that stuff. And how much does that affect things? Well, I find it's actually not very useful to do that, usually. One reason to do it is just so you have less data to manipulate, either because data is expensive or because it's just a hassle. Additive sine wave synthesis is kind of cool, but, when you started with samples, which is a lot of data, and then you did additive analysis, so you have even more data. It's like, oh gosh, at some point you have so much data, even if it's in a nice form, it's still a hassle to try to do anything with it. So there's reasons to, approximate it and do various other things. So, yeah, random variations. The random variations matter. If harmonics are non-random, and this will come up later again, if they change in sync, it doesn't even have to be that all of them are getting louder at the same time, all of them getting quieter at the same time, but if they change in sync, like if some are getting louder and quieter, that they stay synchronized when, say, the slope of their changes and stuff. There's shimmer effects and various other things you can hear that really make a difference in how well a sound fuses and what it sounds like. There's, it deals with if you have multiple people playing, how things interact and stuff. So these little changes you may not hear in a tiny little example like this, but they may matter. There's also sort of, interesting things here. Oh, and one thing about random that you have to watch out for as electrical engineers, people always like to say, oh, this is either, predictable or random. And if it's random, then obviously, you do a Gaussian random number generator. So, there's a lot of different kinds of random. It's kind of like saying, oh, it's predictable, so it must be a sine function. It's, no. It could be any sort of function. And similarly, if it's random, so most things don't get very far with just making randomized properties of it. In fact, as you'll learn later in this course, just simple things like if you go into the C language or Fortran or any of these programming languages, you generate random numbers and play them through a speaker. They sound awful. Now, it may take you a while to listen to it. It'll sound like, random noise sort of, but you hear whistling in it. Your ear actually makes structure in there that isn't there. And you can have the same, first order statistics and a better random number generator that'll sound much better. So be really, really careful that you don't just jump to conclusions, oh, it's random, so it doesn't really matter. I just put some random number generator on it. Yeah, that's not the case. There's sort of this middle ground between there's a lot more to it than our mathematical constructs. Okay, so there's another question here. Can you pitch shift this data and get a full range of the trumpet? Well, that's sort of related to that thing they were asking about formants. The question is the trumpet a system like we like to model voice too, where there's all this kinetic energy in your lungs, lots and lots of energy, right? It goes, your vocal flaps open and close, as the air gets forced through your vocal cords, and then magically becomes a square wave with no appreciable, an acoustic wave with no appreciable air movement, and your mouth is a linear resonator, acoustic resonator, and that's that. Your mouth has some frequency response depending on shape, and that's the end of story. Sort of an okay model, but what happened to all that kinetic energy? Like if it was efficiently converted to acoustic energy, you'd be louder than a foghorn. So it's not, it's not converted to acoustic. A tiny, tiny percentage of all that energy is changed to acoustic, and it would take a pretty gullible person to believe that right at the vocal flaps, it suddenly becomes a acoustic plane wave. I mean, the thing is much, much more complicated. Well, in a similar thing, in a trumpet, you've got your lips flapping in the breeze, and if you want to model the trumpet as just an acoustic resonator, so you're ignoring the flow, the aeroacoustic effects, just an acoustic plane wave, then there should be some, depending on which pitch you're playing, there should be some spectral peaks, and those just shape what's coming through your lips. With one good sample and knowing what the spectral peaks are, you should be able to generate other pitches. And it sort of works a little bit, but it turns out that it is way more complicated. There's all this turbulence, there's all these other things going on. It's not just a linear resonator. In fact, most notably, one of the things that happens is you'll play some low pitch, and there'll be some high frequency that's totally cut out. It's like the instrument has no response at the high frequency. But then if you actually shifted to that high frequency, you'd clearly get the fundamental. So it's not just this fixed frequency response. There's something much more complicated going on. So anyway, can you pitch shift this data and get a full range of the trumpet? Well, the answer is definitely no. You need lots and lots of information. Just like a sampler would just take hundreds of samples. And similarly here, this is basically like sampling, except you did a little extra analysis. Lets you manipulate it more, but you haven't really done anything yet. So you'd have to be smarter about what you do if you want to be able to pitch shift a line. And the same thing. Can you scale the amplitudes and get a full range of dynamics, pianissimo to fortissimo, even at this one pitch? And of course you can. Right? You know that when you hear quiet piano playing, it sounds very different than loud piano playing, or quiet trumpet versus loud trumpet. And if you take a quiet trumpet, somebody playing quiet trumpet, which by the way is quite beautiful, you don't hear it so often, but quiet trumpet playing is gorgeous. And if you crank up the volume of of quiet trumpet playing, it's not going to sound at all like a loud trumpet playing. It sounds like a recording of quiet trumpet that somebody cranked. And it's different issue. So don't, so this is really cool stuff. You can do a lot with additive synthesis. You get a lot of information out of it and stuff. So, it's not bad, but it's also easy to think, okay, we solved all our problems. All right. Any questions about that? I had a few other things. Let's see here. What did I do? Blah, blah, blah. I talked about that. Oh, yeah. Did it make sense why the frequency envelope goes totally insane at the end here? You'll notice this in Fourier transforms and stuff too. If you have no amplitude at some frequency, then some frequency bin in your FFT, there's no data to go on. It's just sort of going on noise, and it's going to produce some sort of random thing. So this is a really common issue that you have, it goes crazy when the amplitude goes low. And it's a real hassle. Like one of the cool things you can do pretty easily with additive synthesis is do sound morphing. So you take a weighted average of amplitudes and frequencies of the different partials of two different sounds, and you get, an in-between sound that actually sort of works. But you end up with all these icky problems like, hey, the one sound has really quiet here, so the average of the amplitudes works fine, but what are you going to use for the frequency? Because the quiet one has insane frequencies because, well, it's too quiet to have good frequency values. So you have to do all these extra tricks to figure out, okay, I want to take a weighted average of the amplitudes of each partial and the frequencies of each partial, except the frequencies also have to be weighted by amplitude or amplitude cubed or whatever you end up doing. And it's just pretty complicated. And even that kind of thing can really backfire on you depending on what you're doing. So, yeah. So, what else? In the beginning of these sounds, you'll see there's this frequency blip in lots of them. That's actually and in amplitude too, you get this thing. Those are sort of typical things for brass instruments, and you really don't see the same thing. They really do mean something. But what exactly they mean really depends on the details of your analysis and all sorts of things. Only comment I have about that is this additive sine wave stuff, especially when you're only using harmonic partials, when you're using short windows like this, works really great for anything that has standing wave pattern. Like pretty much any sustained acoustic instrument, because you're putting energy in there, the standing waves, and that's by far the dominant thing you're hearing. But at the very beginning of a sound, the standing waves, well, they haven't had set up yet. There hasn't been enough reflections to really have a good standing wave pattern yet. So at the very beginning of a sound, you sort of expect some weird things, because you wouldn't really expect there to be a good harmonic sound yet, because you don't have a standing wave pattern set up yet. Does that make sense?
Isn't that kind of the nature of the attack of a brass instrument too? So I feel like if you get like an amateur player, you'll hear the attack and then you'll
It doesn't even. It's almost in the digital world we say it doesn't fuse. It doesn't even sound like it's part of the same thing. It's just sort of a mess. And actually, there's a lot of instruments like this, like a lot of tuned drums, for instance. If there's a sort of extreme, but you hit the drum head, and as you know, it's a two-dimensional vibrating surface, right? It's not going to give you a harmonic thing. But the body of the instrument is a resonator that's going to get you a standing wave pattern inside the body. And that's why, like a kettle drum or lots of drums, are very, very clear pitches. But the attack is all over the map. And it makes for quite a beautiful thing. Again, if it's played well, a beginner might not sound so great, but it can be quite a beautiful thing. And again, those drums, you can analyze them, some of them quite well with just additive sine waves rather than using Bessel functions or something that's more 2D vibration oriented. But yeah, the attacks are always difficult. And one of the other things about your hearing system is, everybody wants your ear just to be this FFT. But actually, your ear is really another way of saying this, your ear is really sensitive to the time domain shape of an attack. And so this is sort of counterpart to your hearing too. The attack is actually, unfortunately for these analysis methods, the most important part of the sound. Like, you got to get the attack right. And it's really hard to do because, for 99% of the sound, it's got a nice standing wave pattern, but not in the attack. Anyway, just some ideas. If you have questions, speak up. Otherwise, I'll go back to our phase oscillator here. Now, the phase oscillator, for instance, in the Egan matrix. Oh, I lied. We do use wavetable oscillators. For instance, in the additive synthesis sounds, the thing that does that modeling phrase that I always play. Those are wavetables that contain sine waves. Just for that purpose, the easiest way I could figure out to do it is to make a wavetable and put a sine in it, and that's way easier than trying to compute a sine, way faster. It's way, And also, a sine wave is kind of easy. As you'll see a little later here, there's a reason why at the bottom of the page I have this thing where you have more and more harmonics in a sawtooth. The nice thing about a sine wave is it's always only got the fundamental. Right? There are no harmonics. So a sine wave is pretty easy because, say, for instance, you want to figure out, well, is this going to alias? Well, it's really easy. You just don't play a sine wave that's over the half sample rate. Just ignore it. And if it's below the half sample rate, you play it. That's really cool. But now let's say you have a more complicated waveform like the sawtooth. Well, a sawtooth has infinite number of harmonics, right? Here's a real sawtooth in the, a sort of a perfect sawtooth in the analog world, not in the digital world, in the analog world, right? It would look like this. It has, which tells you, from Fourier theory, you need loads and loads of sine waves to make sharp corners. In the digital world, you better never see a sharp corner like that. If you're going to synthesize it, you got sharp corners, then you're fooling yourself. It's not what it looks like, right? You don't want to make a sawtooth that looks like that in digital and stick it to your DDA converter. You always make a sawtooth that looks like one of these wiggly dudes. Right? And why is that? Well, you can't have any sharp corners because you can't have frequencies above the half sample rate. And if you say, oh, but I do have frequencies above half sample rate. See this corner here? See, that's sharp. And this is a digital signal. Well, you're fooling yourself. What it really is what that represents, you're misinterpreting it. What that represents is an aliased piece of garbage. You don't want that. You always, when you are going to play a sawtooth, you got to play a sawtooth where you have some number of harmonics in it. And that number should be, like it says here, the highest harmonic, the highest frequency you have. Oh, I should explain what these numbers are first. I should just, I'll get back to this. So what I should say instead is you want harmonics up to the half sample rate. You want partials, all the partials in the sound that go up to the half sample rate, but nothing beyond. And that's a good sawtooth. And that's a real pain to make. A sawtooth is really quite easy to make in analog, but in digital it's a pain because you want to, again, include all the partials, all the sine wave components up to the half sample rate, but nothing beyond. So you can't have any sharp corners. Similarly, if you want to make a square wave in the digital world, you can't just have a function that goes from maximum value to minimum value and then stays at minimum value for a while and goes back to maximum value. That's a piece of garbage. That's not a digital square wave. Right? It would be fine in analog because you don't have a half sample rate in analog. You can do that kind of thing in analog. But in digital, you have to limit it to the half sample rate. What do they call this thing? A Gibbs phenomenon? Do you use that word? No? Yes? I see some of you. Okay. But anyway, so you sort of know this. You've seen this before, but it's really, really, really important in audio. So let's get back to this thing again here. We got this phase oscillator, and I'm going to zoom out just a little bit so I can get the whole thing in there. There we go. So in this phase oscillator, is that readable? Yeah, that's not too bad. We have a frequency register up here. There's an F. And then we have a phase register. So the frequency register and the phase register are both on this. There's different ways to interpret this, but just go with me. We're going to consider them values 0 to 1. Okay? So in digital stuff, that would mean your binary point in the digital system is way on the left. So these values are always 0 to 1. Okay, so you've got this frequency register here, and if you have some frequency in hertz, you can figure out what the frequency register represents. It's 0 to 1 times the sample rate. So whatever is in the F register. Say you want to put 1,000 hertz in there or something. You can, from this formula, figure out what's the F value. Right? Say your sample rate is, 48 kilohertz. It'd be 1/48th. Whatever 48 is in binary. But okay, so this is okay. This frequency register here is the formula for it. Frequency in hertz equals the F register value, which is 0 to 1, times the sample rate. And that's just a formula you want to memorize, you want to know. And it'll actually sort of make sense once you understand the diagram. Are we good? The phase register here is, when I say 0 to, actually I sort of made a mistake. When I say 0 to 1, it's actually 0 to 0.9999999. Pretend you had at base 10 24-digit number. These are binary 24-digit numbers. But, right, the biggest number you can represent in there is all 9s. Well, in binary, the biggest numbers you can represent in there is all 1s. But anyway, yeah, so the phase register is the same way. It's 0 to 0.99999, and that corresponds to 0 to 359.99999 degrees. And just like you're used to, right, 0 degrees and 360 degrees are sort of the same thing. They're aliases of each other, in fact, is one way of saying that. So this represents 0 to almost 1 or 0 to 359.99999 degrees. Does that make sense so far? Okay, so what's going on here? Well, what this diagram, this is called a digital integrator here. And what it does is at each sample time, if you think of this like a sort of an engineering schematic-like thing. You got an edge trigger here, so each sample time, each positive edge of the sample clock, you update the phase register. And what does it get in it? Well, it has its previous value plus whatever's in the frequency register. So all the frequency register really is an increment for the phase register. Sort of makes sense. I mean, if you are, say you play a high-pitched sound, its phase is changing fast because it's higher frequency. Say you're playing a really low-pitched sound, its phase is changing slowly because it's low frequency. Right? So that's all that is. This frequency thing here is proportional to hertz, and if you have a low number of hertz, then this adds in smaller numbers, and the phase goes up slower. If you have a high number of hertz, then the phase goes faster. Make sense so far? There's also a C program version of this on the next page, so don't sweat it too much. If you're into C programming or any programming, it's a really verbose program. I could have written it in 4 lines instead of this and left out some of the comments and some of the other dribble in there. But I think it was sort of clear. And it's a real running program. The output from this program with the parameters I gave it are on the 3rd page of the handout. So you can study that. But this is, an important idea. So why is this called a digital integrator? Well, it's because you keep adding in this F value every time interval. Every sample, you add in the F value. And again, the F value is 0 to 1. The phase register is also 0 to 1. And the way you think of the phase register, what it represents is 0 to 360 degrees through your waveform. It's an exact repeating waveform, so we can talk about, you're 2 degrees into it, or you're 7 degrees into it, or 359 degrees into it. But it's just going to repeat over and over again. So 360 degrees into it is the same as 0 degrees. So that's a digital integrator. Another way of writing this is that the phase register value theta of n plus 1 equals theta of n, where n is the sample number, plus whatever the F value is. Now, if you were to draw this over time, so this time, I didn't draw individual dots here. It's really digital, so it really should be individual dots, but I didn't do that. So imagine the dots. The time is quantized here. It's in sample numbers. And what's happening here is, if you look at the phase register value here, this is just the phase register value. It goes 0 to 1. And over time, it keeps going up and up and up. How fast it goes up, or its slope, as a time function, just depends on F. So this is just a drawing of what the phase register is doing. This looks like a nice sawtooth. It'd be really tempting to give this to your D to A converter, and that would be a real noob move. Don't do that. We'll talk about that more, but there's other things to talk about first. So what all the comments I have here? The phase oscillator's purpose is to make a repeating waveform like a sine, triangle, or sawtooth, or whatever. It can be other things. And I called it a phase register. I admit that I just made up this word, but I couldn't find one that anybody else had. So, and now other people are starting to use it just because somebody needs a word. So it's a phase register. So phase oscillator just means, hey, it's got this integrator here. It's got this thing integrating the phase. All right. There is something important up here where it says wrap. And what is that? That is that if you looked at this thing under a microscope, what you would find out is that this point down here is not exactly the same as this point down here. The actual phase values it computes each time are not the same. What happens is it's adding in this F value, and then it's adding in the F value, it's adding the F value, adding in the F value. When it gets to the top here, it overflows. Right, it goes beyond, goes beyond 1. But what happens is that whatever's left over, so sort of the carry out is just thrown away, but whatever's left over is still kept. So you start the next period at a different phase than you started the previous period. And you have to do that. If you don't do that, you're screwed. Okay? So that's what phase wrap means. It doesn't mean, when you get to the maximum, you jump to 0. No, not at all. What it means is you just ignore the carry out and you just keep going. Just let it overflow and ignore the overflow issue, but keep the drags, keep all the lower bits. I want to do a quick aside here before we go on page, because I don't know, people have different backgrounds, and hey, if this is boring, well, be glad you know something. It's always nice in the ECE class if you already know it and you can kind of relax your brain. This is a phase oscillator, phase wrap and frequency accuracy. I want to talk about this a little bit. One of the things here, I sort of said this before, theta and F, the way we consider them are always from range inclusive 0 to almost 1. I think that's the right, cool, mathy way of writing that. I haven't had to do that since some beginning math class, so I don't know. But does this make sense? People have seen that notation, or is that last millennium? Okay. Yeah, so 0 to 1. So in binary, what does that mean? Well, the phase register, here's just an example of a single add that does wrapping. Okay. So in binary, let's say you were at this value. I put all 24 bits here because, and I drew this on chalkboard actually pre-COVID, and took a picture of it. And the reason I drew all 24 bits is otherwise people get confused. Like if I make a simple example, you can't relate it to the other image. And the other image, I was saying 24 bits are good number of bits. So here's 24 bits, and it says 0.111110100010110101. That's my first number. Okay, that's a pretty big number, right? Because it could only represent 0 to 1, and you can tell here, well, the first 4 bits here are all high. So it's very near, it's very near 360 degrees. Oh, it doesn't ever get to 360 degrees, but it's very near 359.999 degrees. Yeah, maybe this is 357 degrees. I don't know what it is. Some number of degrees. Okay? That's what this phase register is. Now, over here, I have the same thing that I wrote on chalkboard. I just added this, is a hex equivalent. So if you're not familiar with hexadecimal, it's just a shorthand for binary numbers, for base 2 numbers. So you take 4 digits at a time, and you use 0 through 9, and then A, B, C, D, E, F to represent 4 digits at a time. So the first 4 are F, and then you see a 5, and then you see a C and a 0, and you just 4 digits at a time. If you don't know what hex is, you don't have to worry about it. I'm just showing you here, this binary addition is the same here. Now with the binary addition, it works like base 10 addition. It's just confusing because there's only 2 values. In some ways, the hex adding or decimal adding is less confusing. But in the binary addition here, you have 1 plus 1, got you 0. So your new phase value has a 0 at the very bottom bit. And then, but there was a carry, so 0 plus the carry gets you 1. And if you go through all of this, I'm quite sure I have this right because I finally did take a picture of this because I kept screwing it up. And I've decided, this is really dumb to give you errors. But what happens at the very end here, if you look at all of this stuff, in this add you'll find if you actually go through all of this, there's a carry out. So it's trying to be 1.000010, and you just ignore the 1 point. You're only doing numbers 0 to 1, and phase wrapping means you just throw away the top part. Now this makes sense. I mean, you know this from ECE402, right? You have all sorts of situations where you're incrementing the phase, and then nothing magic happens at 360 degrees or 2 pi or whatever system you're using. It just, you can just do mod 2 pi or mod 360 degrees, and that's that. So it's nothing very amazing, really. It's just very important you do this. In decimal, I can represent these things in decimal. Why do that? It's just easier for me to understand. So this is decimal 0 to 1, not 0 to 360 degrees, which would be another, so this was phase on the 0 to 1 scale of 0.959997. There's a question about, are there problems modulating the frequency? And there certainly are. Big pain in the rear. Digital stuff is a pain. I mean, people really like analog signals for a lot of reasons. The cool thing about digital is it's totally repeatable, and once you have your pain resolved, then you can make a gazillion of them really cheap. So it's not all bad. It's just, step one is such a hassle. And step 1 is so hard that many synthesis systems here online don't get step 1 right. So it's kind of too bad. Anyway, so here we have all of these numbers here. They add up to this, and this is all the leftover stuff here. So you can see here this was very near 1, and this is quite near 0 because look at that. This is a fairly high frequency. You know, you can kind of tell, you know, this is somewhere around a 32nd of the sample rate. So if you were going at 48 kilohertz, you know, maybe 2 kilohertz range, somewhere around there. 1 kilohertz, maybe, I don't know. I can't do math in my head. Okay, anyway, whatever it is. Yeah, you know, it's not a fake frequency. It's reasonable. Maybe it's 8 kilohertz. Who knows? Or 1.5 kilohertz. Somewhere in that range. So this is a reasonable addition. So what is the biggest possible value of theta? Again, it's all ones, which is 0.999. What is the biggest F you would ever use? Oh, here's a good question, right? If you look at an F formula, you multiply this big F register times the sample rate. Well, you never want to go above the half sample rate, even if you're playing a sine wave. So basically what it tells you is that for the F register, that first 0 after the decimal point is always going to be a 0. If it ain't, something is really wrong. No matter what you're doing, you're aliasing. So, you know, you would never want to go above the half sample rate. So now there's this funny thing about perfect frequency accuracy. It says perfect frequency accuracy means the top 12 bits of the phase accumulator in the diagram we had are correct after many periods. And so we will look at this in more detail now that we've done a review of binary math. So what is this here? What are we talking about here? Well, it is sort of a weird setup here. I don't know if you've looked ahead, but here this is 24 bits. Phase register 24 bits. I'm sorry, frequency register 24 bits. This pass is 24 bits. You got a 24-bit adder that wraps. That just throws away a carry out. Here you've got 24 bits going in the phase register. This is 24 bits. This whole thing is 24 bits, which seems sort of like a waste because in this waveform, now this example, this isn't what we always use. In fact, the eigenmatrix rarely uses this, only on some occasions. But here we use the top 12 bits to look in a wavetable. So the wavetable's only got 4,096 data points in it. It isn't very big, but it turns out that's enough. Usually your problems come from elsewhere, if, you know. And because of, we'll talk about, you usually have hundreds of copies of each possible wavetable. If you're doing wavetable synthesis that is good quality, it turns out there's reason to keep it short, even, you know, unless you have infinite memory to waste. It doesn't gain you a whole lot to make the wavetable longer. It turns out because this is a band-limited thing in here, almost always, if you really want to make a longer wavetable, you'd be way better off just doing linear interpolation between values on the output. It's not that important, just something to mention. People always like to throw memory at things because they bought gigabytes of memory in their system, but it doesn't really gain you much. Okay, so here's the phase register, and then we only use the top 12 bits. So why even do 24-bit math here at all? And that's, you know, in CS, you might call it guard bits. I don't know what you call it, but it's just so you don't accumulate error. Look, this thing is adding in values all the time. And if you were only to do a 12-bit adder here, then, okay, after the first add, you might be in pretty good shape. But after you add a couple thousand times, it would really not be very accurate at all, right? You'd get a half, you know, you get way off really fast. So these fractional bits here, or I shouldn't call them fractional bits, but you know, you only use the top 12 bits, but it's super important how big to use 24 bits in this. So that's where you get your frequency accuracy. Basically, frequency accuracy means that if you want perfectly accurate frequency, the best you can do in this setup is to have these top 12 bits be the correct value. So let's say you start playing your sawtooth, and you want to check your frequency accuracy, you know, is it perfect? Well, that would mean that after 3 seconds of playing your sawtooth, you are on the exact correct value as if this was infinite accuracy bits. And it turns out you won't be. But 24 bits is enough. Okay? So the only thing that affects frequency accuracy is not how big this wavetable is, Another common mistake people make, you want to make this, make more bits here, then we have better frequency. Wrong. Frequency accuracy only depends on what is the phase. How accurate is the phase over time? So the only thing that affects frequency accuracy is how big are the bit paths here. These are 24 bits. Normally on computers nowadays, people often use 32 bits. Because why not? You got a 32-bit computer. Nobody, well, unless you're doing specifically audio DSPs, you don't see 24-bit numbers very much. Does that make sense? So frequency accuracy, it says here, frequency accuracy is smallest possible frequency change. This is another way to think of it. Well, what is the smallest change you can make in frequency here? You change the least significant bit of f. So there's a little formula here that tells you f delta, which is sort of a symbol that we often use for frequency accuracy stuff. This projector is a lot better than that one, it turns out. Well, I'm just seeing all the lights reflected in it, so it's really hard to read. Anyway, this room has a few design issues. Yeah, the frequency accuracy is the smallest possible frequency change. So the least significant bit of f is 2 to the minus 24, since we've got 24-bit numbers, times your sample rate. Now, when you look at this in hertz, say you got a 48 kilohertz sample rate. Well, 2 to the, that's 16 million. So it's 48 kilohertz divided by 16 million. It's like accurate to a fraction of a hertz. Why bother? Well, take my word for it. It's good. We'll talk about it more later. Plus, you generally don't gain very much. The only thing you could possibly do is use 16-bit values, and those will get you in trouble right away. Reminds me of, Apple has, of course, come a long way, but I remember early on when they made that, what was that loser thing called? The Apple IIe or whatever it was. Before they got all their cool ideas from Xerox, they would have ear training programs where they would play chords for you that were deadly out of tune. And, you were supposed to do ear training with them. Very impressive. Anyway, yeah, so that's because they were trying to do 16-bit math for this stuff. Not good enough. Okay, so we've got this wavetable here. The wavetable itself, these are just reasonable numbers, 4,096 long times 16-bit memory. Now, when you think of a wavetable that's 4,096 long, it doesn't seem like a lot of memory. But let's say you had the example I had before. You're in the lab. Oh, I better see. Oops, I never did post that. Say you're in the lab and you're playing your sine wave generator. And let's say you're running at 44.1 kilohertz, a sample rate. Same as CDs are. A lot of stuff is recorded at that rate still. So 44.1 kilohertz sample rate. And let's say, I don't know, we play a 1,000 hertz sine wave. How many samples are you getting per period? About? 44 kilohertz, 44.1 kilohertz, and a 1,000 hertz sine wave. I'm glad you guys aren't saying anything, because I always get befuddled by stupid little math things. It turns out it's just about 44 samples. You just divide, and it's obvious, right? This isn't higher math. This is AM, and it feels silly to speak up in the middle of a class. But yes, it's just 44 samples. So when this is 4,096 samples, that's actually a lot of samples for a period. Doesn't seem like that much memory, but it's a lot of samples. In fact, if you wanted to sample your sine wave to fill this wavetable directly, you'd be going at really insanely high sample rate. That's totally impractical. So 4,096 is good enough. What is actually happening here? Well, you're stepping through this thing, and if you look at neighboring values in the sine table, say you're doing 1,000 hertz sine wave. Say you filled it with a sine table, or you can put other waveforms in there. Let's see, put a sine wave in there. What's happening here? You're incrementing here. The top 12 bits aren't just incrementing by 1. They're incrementing by some larger numbers. Like if you look at the example I had on page N here, 1, 2, 3, 4, 5. The top 12 bits goes to there. Right, so you got a lot of activity. You're jumping over a lot. You're not just reading every neighboring sample. You'd have to be playing at a fraction of a hertz to do that. So it'd be way, way, way sub-audio if you're hitting every sample. But you're going through there, so you're playing like every nth sample, where n is not an integer, I guess. You're skipping over some samples, you read something out, and then it goes to the D to A converter. Gets a low pass filter, in that process, of course. After convert to analog, you got to get rid of all the high frequency copies of your spectrum, but all that stuff happens and you're good. So that's what that wavetable is doing for you. But you're not reading every sample in here, and that's often confusion here. This is, or you could just think of this as it's implemented as a table lookup, but it's basically just a function, right? It's really quantized, but it's just a function. You can think of just going into any other function. And that's just the phase into it. All right. So, next topic here. This is from Symbolic Sound Kima because I had this nice example. They're also a local company. They've been in the cutting edge business for a long time. I did my undergraduate and graduate with them, with Carlos Scaletti and Kurt Hebel, who run that company. So they have a lot of cool stuff. This is an example of just something where I could take a real system that does this, because the Eigenmatrix doesn't do it this way. So I wanted to find something that, because the Eigenmatrix just computes there. I have different restrictions. The symbolic sound system, Kima, has a lot more memory than I do. I can only use on-chip memory, and so I have to do things differently. But if you look at this thing here, I'm supposed to point out here because people out in virtual land can't see this. So what is this thing here? Well, you want to make it so that your highest frequency in hertz is your F register, whatever your F register is, times sample rate. All this really is what frequency are you trying to play? What's your fundamental frequency, right? Times the highest harmonic number. So if your fundamental frequency, say, is 1,000 hertz, and you have a 48 kilohertz sample rate, how many harmonics can you have? Well, right, 24 times 1,000 hertz is the half sample rate. You don't want to hit that. So you can have up to 23 times 1,000 hertz, up to 23,000 hertz, right? So you have 1,000, 2,000, 3,000, 4,000, 5,000, 6,000, all the way up to 23,000 hertz. You don't want to have anything beyond that. Well, how many is that? So it's 1,000, that's 23. So you would find a table here. This only goes up to 8, but you'd find a table that has 23 of them. And that would be the one to choose if you're going to play something at 1,000 hertz. That's all this formula is saying. And that's why you have to do this. You have to pick one of these because to make a good sawtooth is really important, right? Because a lot of times you use it to filter things, do other things. So a sawtooth has a nice sound to it. And actually, if you have all the partials up to half sample rate, that's out of your hearing anyway. The sawtooth is good. There's not a quality problem here. The quality is if you do it wrong. Then you have a quality problem. What you got to do here then is, or the way symbolic sound does it, they just have this sawtooth here, starting with made of one partial all the way up to 512 partials. It's got 512 copies of it. Pick the one you need. And you don't have to do that when you're using their system. It does all that automatically for you. But it just pre-computes this stuff, and then it's super efficient, right? Then it's just a table lookup. Yeah, you have to use the right table. But you got to be kind of careful even then. In fact, I had the question earlier from Sean about, well, what if you modulate your frequency? Say now you're at 1,000 hertz, and you go down, you're doing a big vibrato, or siren sound or something, and you go all the way down to 900 hertz. Well, now all of a sudden you have a lot more harmonics you got to be playing, a lot more parts. You got to use a different table. And then when you go over 1,000 hertz, you might actually have to 1,100 hertz or whatever you're doing. You might have to pick a different table and do fewer. Doesn't sound too bad, except you can't just jump from one table to the other. You'll have discontinuities, right? So you sort of got to fade one out and fade in another. It's just a hassle. No matter how you do this, it's always a hassle. You can try to only change the zero crossings, which will work in some situations, but usually people fade in one and fade out the other. Does that make sense? Because as you change the frequency you're playing, you need to add or remove partials, because you got, if you're going down in frequency, you've got more harmonics up to the half sample rate. So you got to use a different table. Pain in the rear. Now, if you don't have frequency modulation or very small frequency modulation, you pick one, you stick with it. In fact, online, when you hear a lot of synthesis things, what they'll do is they'll play up to a little bit past the quarter sample rate. And then, you can go up an octave and still be pretty safe. But it doesn't sound like a good sawtooth. I mean, you basically just wasted half your frequency range. Are we good? All right. So, this page, I'm just going to say a few things about it. In the good old days before we did the Echo 360 recording, people would sometimes come up after a lecture and just take pictures of my notes. If you guys want to do that, you're welcome to. If you don't want to scribble this stuff down, or if it's just easier for you, you can just get them out the video later, or you can just scribble it down. To be honest, I always had to write everything down, and it wasn't because I was such a good student. It was because otherwise I'd fall asleep. So, that's sort of up to you. Do whatever works for you. This is a program written in C, and this isn't a C programming class, but most of you are pretty good at some sort of programming. This isn't the most efficient or prize-worthy programming, but it is a program that just plays an A440 hertz note. So A440 is note number 69, or middle A, things that orchestras tune too often. 440 hertz note, and it's generating for a 44.1 kilohertz sample rate. So this is really going to make a sine wave for us. It's just a sine wave. I'll say it's a simple kind of wavetable. Then we don't have to worry about how many harmonics are and stuff, because, well, it's a sine wave. So it's sort of a simple case, but I wanted to give you a program that actually implements that drawing on the other page, because some of you are really, like for me, the drawing is way easier to understand than programming, even though I spend all my time programming. I like drawings. But you know what? I drew that drawing, and so maybe that makes it easier. For you guys, the program might be good. So it's just something to know. Here's a frequency register, and it calls a subroutine to get to frequency. And like the question asked before, if you're modulating the frequency, if it's changing over time, then it makes sense to do that. Actually, in our case, the frequency here is a constant, so it's kind of boring. Boring subroutine. But, okay, so, and then there's an amplitude. Again, our amplitude is constant here, so this is, again, a boring example, but I'm just sort of writing something here. Then this is the phase adder. This is the digital integrator part of it. It's just adding up. And then this is to do the wrapping. I'm keeping it 24 bits in this just because that's what the diagram was. If you actually implemented this, most computers will automatically wrap for you. Unless you tell them, especially if they're digital signal processors, there's also saturation math that they do, and you have to choose which kind of add you want. But usually, you wouldn't implement it exactly like this. You'd actually use 32-bit numbers because there's no harm. And, 24 bits enough, but 32 would work, and you just let it overflow. And you tell it it's an unsigned integer. And I know all that. I'm not totally incompetent programmer, but I wanted to make it the same as what's there. And you can always make a version of this that's 4 lines long and clean it up some. But I just wanted to have all the parts really in the thing here. Here's getting the top 12 bits, and then there's a memory table lookup. And up here I set the memory table at the beginning, so it's all there. It's all sort of pedantic. It is a pretty simple program. I think it's worth your time to actually study it and learn it, especially if you have true interest in digital synthesis. Because, this stuff really matters. And the disappointing thing to me is when I get 395 projects later, like 395 shameless advertising here is project class. You can do whatever you want. I like music projects because I understand them. I can give you more help if you want it. But anyway, I've had many 395 projects where people didn't implement waveforms this way. And, they always sound kind of lame. It's not that hard. Copy this code, change it, sort of figure it out. But in any case, that's a wavetable oscillator there. And in this case here, rather than really give it to the D to A converter, I just do a printf, which is good debugging anyway. You can always get rid of those later. But just see what your sample values actually are when you first do this and graph them or something. So that's what that thing is. Here's output from that thing. And I wrote too much stuff on here. I don't know if I can get a little more of it. So, what do we got here? On the previous page, I already said this. Can I set it all readable? Sort of. 440 hertz sine wave is where we're playing. That's from the previous page program. Phase oscillator sample rate is 44.1 kilohertz. So, you'll notice this 440 and 440.1. Right? What happens is the 440 hertz sine wave is almost 100 samples, but not exactly 100 samples. Okay, it's going to be like never that you exactly divide in the sample rate. Obviously, if you played exactly 441 hertz and sustained it, then yes, for a very short time, you would, things would exactly divide, but we're not doing that. So, what happens here is at sample 0, you see these numbers go up. Now, I didn't scale these. I didn't divide by 2 to the 16th. We had 16-bit numbers in the waveform table, so I just showed them as integers. They go negative, then they go positive. But at sample 100 here, we never see 1004 and 2030 again. The next period through, the first value is 778. And the next one is 1805. And at 200, where they go? It starts at 552 and 1280. Right? So the actual samples you hit each period are different. And it has to be that way. It's always true that if you have an exactly repeating waveform in analog, the sample values are never going to be exactly, well, never except for some pedantic case, going to be exactly repeating in digital. That's super, super important. And, pretend you have your sine wave generator in the lab and you're trying to sample it. So you're going the other direction. You could try to adjust your frequency so that you're, some sub part of the sample rate, a hundredth of the sample rate and get 100 per period, maybe. You'll never be able to twist that knob accurate enough to really hit it. It just doesn't happen. And similarly, when people play music, they're not going to hit exactly that frequency. It's non-starter. One thing that's sometimes useful for people because of this is you can think of the phase oscillator when you go through a table lookup. You can think of the table of being a digital signal, which is super high sample rate, 4,096 per period, and you're resampling it when you step through the wavetable in the phase oscillator. And that kind of resampling works as long as the band limit, as long as you get the right bandwidth. The highest frequencies are good, are less than a half sample rate. We good? This may or may not be a useful thought for you. So if it ain't, that's okay. It comes from a discussion after class with somebody last semester. So yes, so this thing that you'd want to be able to answer, I got to ask you something on exam. So, one thing you want to be able to answer in some way is like, well, why are the values of each repetition period, sample values, different every period in digital? When you haven't exactly repeating things in analog. And if you already understood this the first time I said it, maybe I'm beating a dead horse, but the fact is that this is something where, other professors in the department and stuff, I had to actually prove endless math to show them this, and to me it seems sort of obvious, but people like proofs, so I had to write a proof on the whiteboard. But, and these are smart people, it's just they don't think about this. So it's not a matter of how smart are you, it's a matter of what do you think about, what have you noticed. All right? Uh-oh. I thought I had another page. Oh, I do. Okay, here it is. Okay, so that's the phase oscillator. Now, I want to give you another simple example and do a sound example just because it's kind of fun. I want to do an FM thing, so frequency modulation. Now, I have this diagram here, and there are other ways of implementing this diagram. We'll have much more on this later. This is sort of the easy way to understand it. Not actually the best way to implement things necessarily, but the easy way to understand it. So what is FM music? Well, we got John Chowning, who patented it at 1973. People have been using FM before, for audio certainly. Right? FM radio existed before. So it's not an unusual thing to use, but to have the modulator and the carrier in the audio range is different than radio. Okay, well, people have done that before too, but they didn't really notice it was something that special. So they didn't patent it, they didn't do anything. And John Chowning noticed this is something really special, and you can do lots of stuff with this. He's still around. He's now retired from leading the Stanford CCRMA, but I think he's retired. But in any case, he patented this in 1973, and he really deserves credit for really taking it seriously and really investigating it. I assume you all know the web browser was invented at the U of I, but really, was any part of that new? Well, no. But putting it all together really matters. And really, quote, change the face of the world. So similarly, this is the sort of thing where you can kind of laugh at it. I used to tell people, oh, well, patenting, certain frequencies for modulator and carrier, that's kind of like patenting a certain temperature of bathwater. If your bathtub is at 85 degrees to 90 degrees, that's the perfect bathtub temperature, and I'm patenting that. Well, sort of, but there's more to it here. So what's going on here? You have two phase oscillators, and oh, good. I'm sorry, I have to. That's a bad thing about getting a new toy. You're even more tied to things. Excellent. Anybody know what's the time difference to Paris from here? Okay. So they got 4. Okay, yeah, I got them. Okay, we're good. So what's going on here? Dynamic aviary. 7 hours, thanks. Other world intruding. Brain off. What's going on? Oh, yes. Okay, here. Technical terms. So we got a modulator and a carrier. So we got two phase oscillators. This one's called the modulator, as thus all the subscript M's. And this is the carrier. So before, you can think of it, hey, all we had was a carrier. You had some frequency register here, which some external source might be changing. Maybe your mod wheel is changing. Mod wheel is changing this FC here, or some external source is changing. But when this thing is just running, it's just playing at some frequency. Now, this is your digital integrator, your phase register thing, running at the sample rate. There's some wavetable. We're going to just use sinusoids for this, because it turns out when you do this modulation stuff, yeah, you can use other things, but it just gets to be pretty messy. And there's so many useful things to do with sinusoids. It just turns out what's actually more useful than changing the waveform in here is to use more modulators or use more carriers. Or modulate your modulator, or do other tricky things. And Yamaha went crazy with that after they bought the patent from Stanford, did all sorts of stuff. But we won't go into that. We're just going to do the simple two-phase oscillator, or as that terminology goes, two-operator FM. So what happens here, you've got this guy here, and normally FC determines the frequency. So this is some sine wave playing at that frequency. Well, now you add this in. Let's say FM has a really small value, like, I don't know what, a quarter hertz. Really, really small. 10 millihertz or something. Something really small. And so this is going through really slowly. And it's got some amplitude of the modulation here. What is this doing? Well, sometimes it's adding in positive value offset to whatever your frequency is, and it's adding negative offset to whatever your frequency is. So your frequency is just wobbling over time. It makes a sort of vibrato, right? It makes a low frequency oscillator modulating that. You hear your frequency go up and down and make some sort of vibrato-like sound, sinusoidal vibrato. It may not sound very human, but it sounds like something. Now, that's fine, but that's not what we mostly call frequency modulation. What we're talking about frequency modulation is, what if this is in the audio range, the modulator? Now that's weird, right? If your vibrato speeds up to even a 10 hertz vibrato, you'll sort of hear it. And, as your vibrato gets faster, though, you don't hear it as a pitch change anymore. You start hearing it as just a different timbre. It just sounds like a different thing. It doesn't sound like a sine wave anymore. Now it's a distorted sine wave. In fact, if you look at the thing, you'd see a repeating waveform, and it doesn't look like a sine wave that's slowly changing pitch anymore. It just looks like a different shape. It doesn't look like a sine wave anymore. So that's what this is a very low FM. This is just a low frequency oscillation. It's sort of like a vibrato. But as you go higher, what you end up with is a timbre change, a very useful timbre change. So, so this frequency here, most commonly, FM and FC are actually integer multiples of each other, and that's due to various Bessel function math things. I can prove, we'll prove in lecture 25 that's not important right now. But the important thing is that you pick some FM, you pick some FC, and then over time you change the amplitude of the modulator and the amplitude of the carrier. You get some very effective different sounds. Now, with just two oscillators like this, keeping it this simple, two-wave wavetable oscillators like this, that's really simple, but I think it's quite pretty. And one of the things with FM is the first thing that people try to do, and also the thing that John Chowning did in his patent, is try to say, oh, we can make acoustic-like sounds doing this and that. I'm not sure it's the best way to do, or I'm sure it's not the best way, but that's my opinion. You can have your own to try to imitate acoustic sounds. But FM in itself is quite beautiful. It's one of these things that has continuous change, very different than sampling or something. You have continuous change during a note. You can control how it evolves over time. And that's a big deal. I'm going to play you an example of a little piece with some birdies flying, just to give you something to look at, of Ed Egan playing the dynamic aviary on a just using two oscillators. And the reason I said noodling around, I have a noodling around example I like. When you play a piece of music, right, it's a piece of music and you can listen to it and tell in context. The noodling around examples I often show just are sort of testing something. And it's kind of cool to listen to too, because then you can hear all the different things it does. It's different than hearing a piece of music. Anyway, here's a piece of music. I'll play the video with it. You're not actually watching them play, but it's something to watch. So this is just two oscillator FM, the very simplest kind of FM. And you get timbre changes only by amplitude changes. Yeah, so that's just, straightforward FM, some fixed FM and FC ratios there, and just changing amplitude of the modulator and of the carrier under finger control. And it's quite pretty. I mean, it's obviously electronic, but, that's okay in its own right, too, right? I mean, and not everything has to be an imitation of, cheesy, excuse, I didn't say cheesy, an imitation of something else. I actually do like imitating aspects of acoustic instruments, but I'm somewhat concerned about the modern thing of trying to replace acoustic instruments by the trumpet and the flute button on your synthesizer. All right, so there is, as always, there is. Today is Monday, so the new lab assignment and the new homework assignment is in here. There's some stuff to think about in this assignment. The usual videos to watch and stuff. But I also am concerned. It's easy for people not to take things seriously if they're not, or I should say for ECE students who have been well honed to know that any real homework assignment or any real investigation is a proof or showing some mathematical result. And it's really important you actually, if you want to do anything in music, that you take things beyond that. And so, our engineering school does that. I mean, of all the schools, we're one of the very few, if not the best, at having done something about COVID testing and stuff. And realistically, for each individual faculty member involved, except for maybe the the test procedure itself, but for instance, our physics professor who did the modeling of everything, it's sort of a trivial model compared to other things that he actually writes papers about, but he was able to get together with all these other people in all their different specialties, including people that could raise up tents and do all these other things and organize volunteers, whatever it takes, and actually pull this off. And that's a big deal, and that's unusual for a university. I'm very proud of our university that we can do that. Well, be careful in the lab that you don't fall into the same problem that so many academics fall into, where you ignore things because they're not, some numerical test. You actually want to know the applications of things, but there's a real problem, and there's some thoughts here about how, well, you learned this stuff in 310, and how does this transfer at all to what you actually do in the lab? Because at first, they're pretty separate. And if eventually you can bring them closer together, that's when you've really made it. When you've got sort of a holistic, when math is your tool and not just your goal. And anyway, so that's something to think about. Please read it when you have a chance. And again, like every Tuesday, we also have a new homework assignment. This homework assignment is very different than the last one. So it requires a little bit more knowledge about music. If you don't have the music background for this class, it's up to you. If you have a lab partner, that helps. I realize this semester a lot of people prefer to be alone in the lab just because the COVID distancing issues. But if you can look around or maybe find somebody through the piazza or however you do it, but if you could learn some about the issues in this paper and start early. If you don't have the music background, don't expect somebody to try to make up for your lack of prerequisites, the Monday night. You're not doing yourself or them any favors. And, so this one is about, it's called Optimal Line Break in Music, but it's really about music engraving, about music printing. And, various issues there. It's an important topic to think about because there's all these different aspects of music, and in a survey course like this, I want to touch on these different things. It in itself is a very, very challenging thing. I spent many years of my life on music and in particular also Braille music, but these algorithms are very important and something that's not obvious to somebody who wants to print music or automatically read sheet music. So please think about these algorithms. One of the things that's happening here is a sort of an obvious thing in music. 16th notes are closer together than eighth notes or closer together than quarter notes. Sort of, when they can be. 16th notes are equally spaced. Well, except here, that 16th note isn't equally spaced. And it's not a problem due to rhythm, right? It's the same thing. You got this triple eighths in both cases in the other line. So it's not a rhythm, it's just that cymbals would overlap otherwise. Now, the rhythm does determine some things, like what order are these things in, but, so in music notation, you have this thing that's very different than just our normal written language. It has all the written language issues plus more, because it's a 2D notation, so you have this thing where you try to space things, and there are all sorts of rules about the spacings, but you have to break the rules once in a while. And how you do that really matters, and how readable the music is, and all that kind of stuff really flows from that. So please consider this paper, and I'll talk a little bit more about physics of springs next time, because the paper sort of assumes that you're familiar with springs. And do you guys know that? Like if you have a one spring and you pull on it, it stretches some amount, right? F equals kx. Well, if you got two of the same springs and you pull on it, same force, how much does it move? Well, twice as far, right? Because you got one spring that does F equals kx, another one that does F equals kx, and your force isn't getting lost. It's not, nothing's heating up, right? So if you have two springs in series, the same amount of force moves much farther. But if you have two springs in parallel, the same amount of force moves much less. It's kind of like capacitors and resistors in parallel and series, but anyway, I'll talk a little more about it. I'm out of time today. I'll talk about that next time. Thank you. If any of you are interested in taking pictures, certainly not required, but it also is not unrequired. I will leave them here, or you can just get them online too from the video. I spot checked the video and it seemed pretty good, but I only spot check. Thank you guys for coming. Keep warm. Enjoy the beauty of the snow. Despite the cold, it's still very pretty.